If you're ready to dive into data engineering or want to elevate your Python skills for this field, you've come to the right place. Python has earned its reputation as a Swiss Army knife of data engineering, and today we're going to leverage its versatility. In this video, we'll cover everything you need from foundational programming concepts to advanced ETL pipelines. Whether you're a beginner or seasoned developer looking for a refresher, by the end you'll have the knowledge and confidence to build, deploy, and scale data engineering solutions. This tutorial is built from extensive research into industry trends, essential tools, and best practices in data engineering. I've condensed my years of insights into a practical step-by-step guide. You will find the timestamps on screen, so you can skip sections if you're already familiar with certain topics, although I think it would serve as a great refresher to go through them as well. Here's the breakdown. Section 1 and 2 contain the introduction to Python and the environment setup. This contains what data engineering is, Python's role, essential libraries, and setting up the environment with sample datasets. Sections 3 to 5 contain the core Python skills for data engineering, which is the basics of Python programming, handling essential data structures like lists, dictionaries, and tuples, and file handling techniques with CSV, JSON, Excel, and Parquet formats. Sections 6 through 7 focus on data processing with Pandas and NumPy, which includes data manipulation, cleaning, aggregation, and visualization with Pandas, and numerical computing with NumPy for array operations, statistics, and indexing. Section 8 is all about working with dates and times, that is parsing, formatting, and working with date-time data in ETL pipelines. Sections 9 through 11 cover APIs, object-oriented programming, and building ETL pipelines. In section 12, we cover data quality, testing, and code standard, which includes data validation techniques, unit testing, and maintaining code standards with tools like Flake 8 and Great Expectations. Section 13 is all about building and deploying Python packages, where we create, build, and deploy Python packages which will make your code reusable and scalable. Before we start, if you want more data engineering tips and resources, don't forget to subscribe and turn on notifications. I post new videos every week. I also want to let you know that the complete notebook that is used in this tutorial is linked in the video description. You can download it and follow along step by step to ensure everything works seamlessly on your end as well. Now, in this section, we'll set up the Python environment and demonstrate how to create and manage various datasets in various formats. By the end of this section, you will understand the process of preparing a working directory, generating datasets, and saving them in specified formats. For this entire tutorial, I'll be using Google Colab. To use Colab, you simply have to create a Google Colab account using your Google account. And once created, simply click on the new notebook button to start a new Jupyter notebook. Now let's set up our Python environment. In Python, libraries are pre-written code modules that simplify complex tasks. For example, instead of writing code for matrix operations from scratch, we can use the NumPy library. To use a library, we simply import it using the import keyword. Libraries like Pandas and NumPy are particularly useful for data analysis and numerical computations. We begin by preparing the directory for saving datasets. This step involves checking if a specific folder exists in your workspace and creating it if it doesn't exist. This ensures that all your datasets are stored in one location, keeping the workspace organized. We then generate multiple datasets, each designed to mimic real-world data formats and scenarios. The Titanic dataset is a sample dataset inspired by the Titanic passenger manifest. Key features include passenger details like ID, name, class, and survival status. We on purpose include missing values and duplicate entries to reflect real-world challenges. We then create the employee data, which is in JSON format. This represents nested and hierarchical data often seen in APIs. Each employee has attributes such as the name, department, and salary. It includes a list of projects showcasing how JSON handles structured data. Sales data is in Excel format. It is a time series dataset with daily sales records. It has columns for date, sales, sales figures, and product names. This highlights Excel's suitability for tabular and business-related data. Next, we create user purchase data in the Parquet format. The Parquet format is optimized for analytics queries and storage efficiency. We include fields like the user ID, age, location, and purchase amount. Product data is a straightforward dataset listing the products. Key features are columns like product name, price, and stock availability. Weather data is a CSV which tracks weather patterns over time. This has columns for timestamps, temperature, and humidity levels. Understanding different data formats is crucial for data engineers as each format is suited for specific applications. Preparing datasets helps practice common tasks like data cleaning and aggregation. In section 3, we will dive into Python's basic concepts such as variables, operators, and control structures, which are essential for processing these datasets effectively. Welcome to section 3. In this section, we'll explore the foundational elements of Python programming that are essential for data engineering. These concepts include variables, data types, operators, control structures, functions, and string manipulators. By the end of this section, you'll have a clear understanding of Python's building blocks, which you'll frequently use while handling data. Now let's look at variables and data types. What are variables? Variables are placeholders for storing data values. Allow us to name data for easy access and manipulation later. Think of variables as labeled storage boxes where you can place information. Common data types in Python include integer, which represents a whole number such as 10 or 42, used for counts or IDs. Float, which represents a number in decimal points, for example 3.14 or 7.5, used for measurement or calculation requiring precision. Strings represent text, for example Alice or data engineering. These are used for names, description, or categorical data. Boolean represents true or false. It is commonly used for conditional checks. Python is a dynamically typed language. That means you don't have to declare what type of variable you want explicitly. Python infers the type based on the values assigned. For example, if you assign 10, Python considers it an integer, and if you assign 10.5, it's automatically treated as a float. Now let's look at operators. Operators perform operations on variables and values. Python supports different types of operations, for example, arithmetic operations, where you can perform mathematical calculations like addition, subtraction, multiplication, and division. For example, you can calculate total sales or average metrics. Operators like addition can behave differently based on the data type. For numbers, it performs addition, while for strings, it joins or concatenates them. Similarly, operators like star can work on strings to repeat them a given number of times. This adaptability makes Python very versatile. We can also do comparison using operators where we compare two values and return a Boolean result that is true or false. For example, double equal to checks if the value are equal and greater than checks if one value is greater than the other. For example, we could use this for filtering rows in a data set based on a condition. For example, we could find rows where multiple criteria are met, such as age greater than 30 and salary greater than 50,000. Control structures allow us to control the flow of our code, enabling us to make decisions and repeat tasks. Conditional statements such as if, else if, and else execute specific code blocks of code based on condition. For example, if a product stock is greater than 100, label it as high stock. You define the conditions and Python evaluates them in order until one is satisfied. Loops are used to iterate over collections like lists or dictionaries. For example, using the for loop, we iterate over the product names and print one after the other. Each item in the collection is processed one at a time. While loops are used to repeat a block of code as long as a condition is true. For example, print numbers until a counter reaches 3. The condition is checked before each iteration. Now let's talk about functions, modules, and packages. What are functions? Functions are reusable blocks of code that perform specific tasks. They can accept inputs, that is arguments, and return outputs. We use functions because we want to avoid code repetition and make code more organized and readable. To define we define a function with a name and optional parameters. Inside the function, you write the logic or operations to be performed. You call the function whenever you need to perform that task. Modules are Python files that contain functions, classes, and variables. For example, we could use the math module to calculate square roots. Packages are collections of modules grouped together. For example, Pandas and NumPys are packages used for data analysis in numerical computing. Panda functions are small, anonymous functions defined in a single line. They are very useful when you need a simple function for a short duration, such as when applying a transformation to data. Unlike a regular function defined using def, a lambda function does not need a name, and it is ideal for short throwaway tasks. Now let's look at the syntax of the lambda function. The lambda keyword is followed by one or more arguments separated by commas and then a colon. After the colon, you write a single expression that the function will compute and return. For instance, add two numbers, you could write lambda xy colon x plus y. Let's look at some examples to understand how the lambda function works. In the first example, we use the lambda syntax to define an anonymous function that adds two numbers. The lambda x comma y colon x plus y function takes two arguments x and y, adds them together and returns results. The result of adding 3 and 5 is printed. Next, we use the map function with lambda function. The map function is a built-in Python function that applies a given function to every item in an iterable, such as a list. The lambda function x colon x star star 2 takes one argument x and returns its square. When we use a map function with lambda, it squares every number in the numbers list. Finally, we show another example of using the map with lambda to convert a list of words to uppercase. Why manipulate strings? String manipulation is vital in data cleaning, where data must be standardized. We can do various operations such as concatenation, where we combine two or more strings. For example, we could join a greeting with a name to create a personalized message. We could also format our data where we embed variables into strings using f-strings. For example, including a person's name and department in a sentence dynamically. We can also use slicing to extract specific parts of a string using index ranges. For example, the index 0 indicates the first element and the last element mentioned in the range is not included. So when we write colon 3, it excludes the last element, that is the fourth element, and takes the first through third element. Methods such as lower convert a string to lowercase and upper converts a string to uppercase. Replace replaces occurrences of a substring with another. Errors are inevitable in our code, especially when dealing with real-world data. Handling errors ensures that our program doesn't crash unexpectedly. We use a try block to write code that might raise an error. We use the except block to catch and handle specific errors. Optionally, we could use else to execute code if no error occurs. We use the finally block to execute code that must run regardless of an error. For example, we read a file that doesn't exist. The program should display an error message but continue running without interruption. In this section, we covered Python's core elements such as variables, operators, control structures, functions, string manipulators, and error handling. These building blocks are the foundation for writing scripts that process and analyze data efficiently. In section 4, we'll be discussing Python's built-in structures such as tuples, lists, sets, and dictionaries. These collections are essential for organizing and manipulating data in Python, especially for data engineering tasks. We'll explain how each collection works, their key characteristics, and practical use cases. Now let's get an overview of Python collections. Python collections allow us to manage data efficiently by grouping values together. Each type has unique properties and is suited for specific scenarios. Tuples are ordered and immutable, ideal for data that must remain constant. Lists are ordered and mutable, used for dynamic sequential data. Sets are unordered and unique, great for eliminating duplicates and performing fast membership tests. Dictionaries are key value pairs, ideal for structured data that needs fast lookups by key. Now let's look at what tuples are. Tuples are an ordered collection of data that cannot be modified after creation, that is immutable. They are commonly used when the structure of data is fixed and should not change. Immutability guarantees that once you create a tuple, you cannot add, remove, or modify elements in a tuple. You can access elements using their index just like lists. Tuples are ideal for storing constant data like coordinates or RGB value for colors. In our script, tuples store the coordinates for London. By accessing elements using indices, the script retrieves latitude and longitudes. This demonstrates how tuples provide a simple way to store and reference immutable data. Lists are ordered collection of data that grow, shrink, or can be modified. They are one of the most versatile data structures in Python. You can add, remove, and update items, and you can access elements using indices or extract parts of a list with slicing. Lists automatically resize when items are added or removed. Lists are perfect for maintaining an ordered sequence of items, such as a list of products or file paths. In our script, we create a list of product names, that is widget A, widget B, and widget C. To add an element, we append a new product, that is widget D, to the list. We can also remove elements from the array, and we remove widget B in this example. Finally, the script prints the updated list, demonstrating how lists are dynamically and easily modified. Sets are ordered collection of unique items. They are optimized for eliminating duplicates and performing operations like union, intersection, and difference. If duplicate values are added in sets, they are automatically removed. Elements are stored without a specific order, so indexing is not possible. We can perform set operations such as union, intersection, and difference. Sets are great for deduplication or checking membership. In our code, we create a set of product IDs. The duplicate ID 101 is automatically removed. To add elements, we use the .add. The final set is then displayed, illustrating how sets ensure uniqueness and are well suited for managing IDs or other unique values in data. Dictionaries store data as key value pairs, making them ideal for structured and easily accessible data. For example, you can map product IDs to the corresponding names or prices. Each key in the dictionary maps to a value. Keys and values can be added, updated, or deleted. You can retrieve values quickly using the corresponding keys. Dictionaries are perfect for tasks requiring labeled data, such as for storing user profiles or product catalogs. In our script, we define a dictionary to represent a product. The keys are product ID, name, price, and stock. The values are the corresponding data for each attribute. This script retrieves the product name and price using their keys. The stock count is updated to 120 and a new key category is added with the value gadgets. Dictionary is then printed, showing how it allows easy organization and access to structured data. Choosing the right data structure can optimize our code for both performance and readability. We would use tuples for fixed data, lists for ordered and modifiable collections, sets to ensure data uniqueness, and dictionaries for key value mappings. In this example, we provide a practical example of a list of sales records. Each record is represented by a dictionary with keys like dates, products, and sales. By iterating through the list, the script calculates the total sales for each product. This demonstrates how lists and dictionaries can work together effectively. These collections form the foundation of Python programming, and the mastery of them is essential for handling data in any project. Now let's move on to section 5. Section 5 is all about file handling in Python. File handling is an essential skill in data engineering. It enables us to read, write, and manage data in various formats. In this section, we'll explore how Python handles text files, CSV files, JSON files, Excel files, and Parquet files. By the end, you'll understand how to work with each of these file types efficiently and why each format is suited for specific tasks. Text files. What are text files? Text files are the simplest file format, storing plain human readable text. They're often used for logs, configuration files, or lightweight data storage. Text files can be created or overwritten by opening a file in write mode. To read from text files, we open a file in the read mode, that is R mode, to retrieve its contents line by line or as a string. We can also append to text files using the A mode. Text files are ideal for lightweight tasks like storing logs or configuration details. In our script, we create a text file called sampletext.txt and write lines like hello data engineering into it. Then we reopen the same file and read its contents, displaying it. This demonstrates how Python can handle basic file operations seamlessly. CSV files are widely used for storing tabular data. Each row represents a record and columns are separated by commas. These are human readable and compatible with most data tools. We use Python's Pandas library to write data to a CSV for structured tabular storage. Pandas also allows you to read CSV files and load their contents into a data frame. CSV files are excellent for exchanging small to medium sized data sets between applications. In our script, we create a data frame representing products with columns like product, price, and stock. Then we write it to product_data.csv. While reading the file back, the script displays its content in a tabular format. showing how CSV files are an efficient way to manage tabular data. Now let's move on to JSON files. JSON, that is JavaScript Object Notation, is a structured file format for storing hierarchical data. It's human readable, lightweight, and widely used in APIs and configuration files. To write to JSON files, we use Python's JSON modules to create a JSON file from dictionaries or lists. JSON module can also parse JSON files into Python objects like dictionaries or lists, vice versa. JSON files are ideal for nested structured data like configuration settings or API responses. In our script, we define employees' data, including nested fields like projects, and write them back to employees.json. Then we read these files back and print its content, showing how JSON allows for storing and parsing of hierarchical data. Excel files are widely used in business for data sharing and reporting. They support multiple sheets and allow for formatted tabular data. We can use Pandas to write a data frame to an Excel file, and we can similarly use Pandas to read Excel files back into a data frame for analysis. Excel files are commonly used for sharing data with non-technical stakeholders or for small-scale reporting. The script creates a data frame with columns like date, product, sales, which represent the daily sales record, and save it as sales_data.xlsx. It reads the file back and displays the records, illustrating Excel's suitability for data storage and exchange. Parquet is a binary columnar storage which is optimized for large datasets. It's ideal for analytics workflows due to its efficient compression and fast querying capabilities. Pandas to write a data frame to a Parquet file and vice versa read Parquet files into data frames. In our script, we create the user purchase data, which includes fields like the user ID, age, and purchase amount. We then save it to user_purchases.parquet. This section, text files are best for lightweight data like logs. CSV files are ideal for small to medium tabular data. JSON files are excellent for hierarchical or nested data. Excel files are widely used in business for reporting. Parquet files are perfect for large datasets due to their efficiency. Mastery of these file formats ensures that you can handle diverse data types, whether they are lightweight logs or massive analytics datasets. In section 6, we'll be discussing data processing with Pandas. Pandas is one of the most powerful libraries in Python for data manipulation and analysis. In this section, we'll cover an introduction to Pandas and data frames, data cleaning and pre-processing techniques, data manipulation and aggregation, and basic visualization for quick insights. By the end of the section, you'll understand how to effectively process and analyze data using Python. Let's understand what Pandas data frames are. A data frame is a two-dimensional tabular structure in Pandas. It is similar to a spreadsheet or database tables. It contains labeled rows and columns, making it easy to access, manipulate, and analyze data. When a dataset is loaded into a data frame, this dataset contains information about passengers, including their age, class, and survival status. By using the head method, the first few rows of a dataset are displayed, providing an overview of its structure and contents. Rows represent the individual records, and columns represent attributes of the data such as age or fair. This sets a foundation for exploring and transforming data. Now let's look at data cleaning and pre-processing. Why is cleaning important? Real-world datasets often have missing values, duplicates, or inconsistent formats. Cleaning ensures that the data is accurate and actually ready for analysis. Now let's clean our data. The very first thing we do is check for missing values. Missing values can skew analysis, so identifying them is the first step. We can use the isNull.sum function to count missing values in each column. For handling missing values in the age column, missing values are replaced with the median, ensuring no empty values remain, maintaining data integrity. For the fair column, rows with missing values are dropped as they are considered critical. Duplicate rows are removed to ensure data consistency using the drop duplicates method. After cleaning, the script verifies the absence of missing values and duplicates, ensuring a clean data set is processed. Now let's look at data manipulation and aggregation. Data manipulation involves modifying data to suit specific analysis needs, such as filtering, sorting, or aggregation. We can filter passengers with fares greater than 50, demonstrating how Pandas can quickly subset data. The dataset is sorted by the age column in descending order, making it easier to identify the oldest passengers. We can also aggregate the data by passenger class and calculate the average fare and age for each class. This provides insight into how passenger demographics and fares vary across classes. These operations show how Pandas enables efficient exploration and summarization of data, which is crucial for decision making and reporting. Visualizations help uncover patterns, trends, and outliers that are difficult to spot in raw data. In our code, we create two visualizations, that is, a age distribution histogram, which shows the passengers' ages, helping identify the most common age groups. We also show the average fare by class, which is a bar plot, which highlights the key differences in ticket prices across classes. Pandas simplifies data cleaning by handling missing values and duplicates. It enables data manipulation tasks like filtering, sorting, and aggregation. It also helps us quickly create actionable insights using visualizations. In this section, we'll explore NumPy, the library at the heart of numerical computing in Python. It provides efficient tools for handling arrays and performing mathematical operations. Here's what we'll cover: the basics of NumPy arrays, array operations, indexing and slicing, linear operations, and statistical functions. By the end of this section, you'll understand how to perform fast and efficient numerical computations using NumPy. Let's understand the basics of NumPy arrays. NumPy arrays are similar to Python lists but are optimized for numerical calculation. They store elements of the same data type and support a wide range of mathematical operations. In our script, we create a one-dimensional array from a list. This is ideal for representing simple sequence of numbers. A two-dimensional array is created from a list of lists. This represents a matrix-like structure often used in linear algebra or image data. Python arrays are faster and more memory efficient than Python lists. Each array also has attributes, that is, properties like shape, size, and data type, which can be accessed to understand its structures. Array operations allow you to manipulate data efficiently. With NumPy, you can perform operations on entire arrays without the need for loops. In our script, we perform addition and multiplication to each element of two arrays. This is useful in scenarios like scaling or combining datasets. Mathematical functions like square root are applied to all elements, simplifying complex transformation. Instead of iterating over elements, NumPy applies the operation to the entire array. This significantly speeds up calculations. Indexing and slicing lets you access or modify specific sections of an array, making it easy to isolate or analyze subsets of data. Slicing helps us select sections of array that are selected using ranges, such as the first three elements. Boolean indexing are conditions that are applied to filter elements, such as selecting values greater than 25. In Python, arrays, lists, and data frames use zero-based indexing, meaning the first element is indexed at 0. You can also slice arrays using ranges. For example, arrays 0 to 3 retrieves the first three elements. Negative indexing lets you access elements from the end, while methods like ilock in Pandas allow for more advanced indexing. We can also perform linear algebra operations like matrix multiplication and solving equations that are essential for numerical analysis. In our script, we show an example of how matrix multiplication can be done in Python. Two matrices are multiplied to compute their dot product. This is widely used in transformations and neural networks. NumPy provides built-in functions for solving equations of systems of linear equations as well. Statistical functions also help us summarize data, identify trends, and understand distributions. In our script, we calculate the mean and median, which provide measures of central tendency. Standard deviation and variance is also calculated, which indicates the spread of data. We also do a cumulative sum, which calculates the running total of elements. These functions process entire arrays efficiently, delivering quick insights into data distributions and patterns. NumPy arrays are efficient and versatile tools for numerical computations. Array operations like slicing and indexing simplify data manipulation. Built-in functions support advanced mathematical and statistical tasks. In section 8, we'll explore how we can work with date and times. In this section, we'll delve into handling date and times in Python. which is a crucial skill for managing time series data, scheduling, and logging. In this section, we'll explore parsing and formatting datetime data, common datetime operations, and handling datetime data in ETL pipelines. By the end of this section, you'll understand how to parse, manipulate, and analyze datetime data efficiently. Parsing is converting a datetime string into a Python datetime object, which is structured and easily manipulated. Formatting is transferring vice versa, that is, a datetime object back into a string, often used to display it in a specific format. In our script, we parse a datetime string into a datetime object using predefined format codes. We use codes like percentage capital Y for year, percentage small m for month, and percentage small d for day. These define how the strings are interpreted. We also format the datetime object and it's converted back into a readable string with specific formatting codes. We can customize the output format to suit various reporting needs. Parsing ensures uniformity and allows calculations, while formatting makes datetime human readable. Manipulating dates and times is essential for tasks like scheduling, calculating durations, and filtering data with specified ranges. We can add or subtract time intervals to calculate future or past dates. For example, adding 5 days to today's date helps schedule tasks or events. We can also extract components, which is a common task. You can access specific parts of the datetime object, such as the year, month, or day. This is useful for grouping data by month or analyzing trends over time. We can also calculate time differences between two datetime objects to find durations. For example, we could calculate the number of days between two events. Using built-in functions like time delta, these operations are straightforward and efficient. They eliminate manual calculations and ensure accuracy. In ETL workflows, datetime data often needs to be extracted, transformed, and loaded for a time-based analytics or reporting. In our script, while loading data, datetime columns may initially be strings. Passing them into datetime objects ensures consistency and enables further analysis. We can also filter by date range, where data is filtered to include only rows that fall within a specified time frame. This is useful for extracting relevant subsets such as sales data or a specific month. We can also calculate time differences between rows to analyze gaps or intervals such as time between successive purchases. These operations are critical in processing datasets like time series weather data or transaction logs, ensuring the data is clean and accurate for analysis. Section 9 is all about working with APIs and external connections. In this section, we'll explore APIs, that is application programming interfaces, as a critical tool for data engineers. APIs allow us to fetch data from external sources such as web services or cloud platforms. In this section, we'll talk about setting up and making API requests, handling API responses and errors, saving API data for future processing, and building a practical API data pipeline. Additionally, in this script, we'll use environment variables, which allow us to securely manage sensitive data such as API keys. By the end of this section, you will know how to interact with APIs, securely manage credentials, and integrate APIs into data pipelines. In this example, we use the weather API, which gives us weather information. To set up a weather API account, you can simply sign up with your email. After signing up, you get a free API key, which you can see that I'll be using as well. To store this API key, we shouldn't hard code it in our scripts. To store credentials, we use environment variables. We create a .env file to store API keys or other credentials securely. This keeps sensitive data out of our code base, reducing the risk to exposure. We use the python/.env library to load these variables into our script at runtime. To access the keys or secrets in our script, we use the os.getEnv function. This ensures sensitive data is only available when needed. We first define API endpoint and parameters. The endpoint is the URL of the service that you are accessing, while parameters specify what data you want. Specific parameters that an API accepts are usually available in the API documentation. If we make an API call using the request library, a GET request fetches data from the API. The request includes headers and parameters, ensuring authentication and specifying query details. The API returns data, usually in JSON format. JSON is then passed into Python dictionaries, making it easy to work with in the future. APIs can fail due to invalid API keys, network issues, incorrect parameters, or server errors. Hence, it's very important to handle these errors in our script. We check for the status response code. HTTP status response codes indicate success, such as 200 being OK, or errors such as 404 being not found, and 500 being internal server errors. We can use try except blocks to prevent our script from crashing due to unexpected issues. For example, a timeout error is handled gracefully by retrying or logging the issue. We can raise errors for bad responses using raise for status. We can ensure that any error code triggers an exception, allowing us to handle it effectively. We can also set a timeout for API calls to prevent our script from waiting indefinitely if the API does not respond. The data received from APIs is often used for further analysis, so saving it in a structured format is essential. The API may return large dataset, but you only select the few attributes that you need. For example, we could select the temperature, humidity, and condition from the weather data. We would next create a data frame where we organize the extracted fields into a Pandas data frame. This makes it easy to analyze or save in the future. At the end, we also save it to a CSV for persistent storage and future use. An API pipeline integrates data retrieval, transformation, and storage into a seamless workflow. For example, fetching weather data from multiple cities, processing it, and saving it to a central file. In our script, the first step is the extract step, where we fetch data from the weather API by specifying city and key. We handle errors during the extraction process to ensure reliability. The transform step processes the raw API responses by selecting relevant fields and standardizing them. We also clean and format the data to match our analysis and storage requirements. The load step saves the transformed data to a CSV, appending new records to avoid overwriting existing data. Now, this pipeline can be scheduled to run daily or hourly, ensuring updated data is always available for analysis. This demonstrates an end-to-end integration of APIs into our data engineering workflows. In this section, we dive into the principles of object-oriented programming, which is a foundational concept for Python. Object-oriented programming allows you to structure your code into reusable, maintainable, and modular components. This section includes talking about classes and objects. By the end of the section, you'll understand how object-oriented programming enables data engineers to build scalable and reusable workflows. Now let's understand classes and objects. A class is a blueprint for creating objects. It defines the attributes, that is the data, and the method, that is the functions, that belong to an object. An object is an instance of a class representing a specific entity with its own data. In our script, we define a class called passenger, which has attributes like passenger ID, name, age, passenger class, and survived. These attributes represent the details of a Titanic passenger. We then create an object using the init method, which initializes its attribute with specific values. For example, we create passenger 1 with more specific details about their name and age. Methods define behaviors for the class. In this case, display info method returns a formatted string with the passenger details. Classes allow you to organize related data and behaviors in one structure. Objects make it easy to create multiple instances with similar functionality but unique data. Object-oriented programming relies on 4 core principles: encapsulation, inheritance, polymorphism, and abstraction. Let's break them down. Now let's break down the OOP concepts with analogies. For encapsulation, think of a capsule that protects its content. Similarly, encapsulation hides the object's internal state and only exposes necessary parts. Inheritance is like inheriting traits from parents. A class can inherit features from another class. Polymorphism allows different objects to respond to different methods in their own way, like a universal adapter. Abstraction is similar to using a coffee machine. You interact with the buttons, that is the interface, without worrying about the internals. Encapsulation restricts direct access to some attributes, making data more secure and methods more controlled. In our script, we create private attributes like the passenger ID to ensure they are not modified directly. Getter methods like getPassengerID are used to access private attributes safely. This protects sensitive data and ensures controlled access. Inheritance allows a class that is a child to inherit attributes and methods from another class that is the parent. In our script, we define a person class with common attributes like name and age. The passenger class then inherits from a person, adding specific attributes like passenger class and survived. This promotes code reusability and reduces redundancy by defining shared functionality in parent classes. Polymorphism allows different classes to share a method name but provide unique implementations. In our script, different classes, that is the passenger and crew member, implement the info method in their own way. A loop iterates over a list of objects, calling the info, and each object responds with its own version of the method. This enables flexibility by allowing methods to adapt based on the object's class. Abstraction hides the implementation details and exposes only the essential functionalities. In our script, we abstract the base class data loader, which defines a method load data without implementation. Concrete classes like CSV loader and JSON loader provide specific implementations. This simplifies the interaction with complex systems by focusing on what the class does rather than how long it does it. Let's really understand why object-oriented programming is needed in data engineering. OOP principles help create modular, reusable, and scalable code, which is essential for building ETL pipelines, managing data workflows, and handling large systems. In our script, we create three classes, that is extract, transform, and load. Each class represents a step in the ETL process, encapsulating its logic. The extract class simulates data retrieval, returning a dictionary of raw data. The separation of this step allows for flexibility in fetching data from different sources. The transform class processes raw data, such as converting names to uppercase or standardizing formats. Modularity ensures the transform logic can be modified independently. The load class handles the saving of transformed data to storage such as databases or files. Separating this logic allows for flexibility to load data into different systems without affecting the extraction or transformation step. We can combine these steps and create a workflow which uses the extract, transform, and load classes sequentially to process data, showcasing how object-oriented programming can simplify complex workflows. Object-oriented programming provides a structured approach to code organization, improving reusability and scalability. Principles like encapsulation and inheritance ensure secure and efficient workflows. Polymorphism and abstraction simplify complex logic, making the code flexible and easy to extend. In section 11, we'll be combining the extract, transform, and loading concepts to build a complete ETL pipeline. By the end, you'll understand how each of these steps integrates into a seamless workflow. We'll be talking about the ETL workflow and doing a practical implementation of each step. Now let's look at the extract data step. The extract step retrieves raw data from various sources such as databases, files, or APIs. This step is critical because it brings in the data that the rest of the pipeline will work on. In our script, the function expects the file path as input. This allows flexibility in extracting data from various sources. The function also ensures that if a file is missing or corrupted, pipeline doesn't crash and instead logs the error and continues. Once the file is successfully loaded, the extracted data is returned as a Pandas data frame. The transform step involves cleaning, modifying, and preparing data for analysis. This ensures that the raw data becomes structured and consistent. In our script, we handle missing values, such as the missing age is replaced with the average age, ensuring the dataset remains usable. The missing fare is replaced with the median fare to handle outliers effectively. We also remove duplicates and we drop them to prevent redundant data from skewing analysis. We also standardize formats like text columns like name and sex are reformatted for consistency. Names are capitalized and genders are converted to lowercase. We can also add derived columns. A new column, that is age group, is introduced, categorizing passengers based on their age. This step enables grouped analysis, such as understanding survival rates by age group. The load step saves the transformed data to a target destination, such as a database or a file. This final step makes data ready for use. In our code, we have created a function which accepts the destination file path. This allows flexibility in where you want to write the data. The transformed data is saved as a CSV file, ensuring its accessibility and portability. The function also ensures that issues like permission errors or disk space problems are logged rather than causing the pipeline to fail silently. Now let's bring this all together in the form of ETL pipeline. The pipeline integrates the extract, transform, and load functions into a single workflow. The extracted data is passed through the transformation step, and the clean data is then saved. The modular design ensures the pipeline can handle different data sets with minimal changes. Errors at any stage are logged, ensuring the pipeline is robust and easy to debug. When running the pipeline with the Titanic dataset, we extract the data from the raw CSV file, clean and prepare the data, and handle missing values, duplicates, and formatting consistencies. At the end, we save the clean data into a new CSV file ready for analysis. ETL pipelines streamline the process of preparing data for analysis. Modular steps for extraction, transformation, and loading ensure flexibility and reusability. Handling errors at each stage improve the pipeline's robustness. In section 12, let's look at data quality, testing, and code standards. This section emphasizes ensuring high quality data through validation, implementing rigorous testing for pipeline functions, and adhering to coding standards. By the end of this tutorial, you will understand data validation techniques which ensure datasets meet expected criteria, testing data pipelines using unit tests to validate pipeline functionality, advanced quality checks using tools like Great Expectations, and static code analysis which ensures clean and maintainable code with tools like Flake-it. These practices are essential for building robust and maintainable data engineering workflows. Now let's look at data validation techniques. What is data validation? Data validation ensures that datasets meet predefined quality criteria, such as completeness, consistency, and accuracy. This step is crucial for preventing errors from propagating throughout the data pipeline. In our script, we check for missing values. The dataset is scanned for empty or NaN values in each column. We identify and address these gaps to ensure analysis aren't skewed by incomplete data. We also validate column data types. Columns are checked to confirm they contain the expected data type, that is numerical or categorical. This step ensures that the operations like aggregations or computations won't throw errors. We also check unique values. Specific columns such as passenger ID are validated for uniqueness to avoid duplicates. For categorical data like sex, the script checks whether all entries belong to allowed categories. Validating data early in the pipeline ensures that errors are caught and corrected before they affect downstream processes. Testing data pipelines with unit test. Unit test is a Python library for testing individual components of your code. It helps ensure that each function in your code behaves as expected. In our script, we set up the test data. We create a sample dataset with known issues, that is, with missing values and duplicate data. Tests verify that the missing data are handled correctly. Duplicate rows are confirmed to be removed during the transformations. We also validate new columns. The presence and accuracy of the right columns, such as age group, are tested. Text columns are checked for standardized formatting, that is, the names are capitalized. Assertions are used to confirm that the missing values no longer exist. All duplicate values are removed. The transformed data adheres to its expected formats. Testing ensures that your pipeline functions correctly even as data sets or requirements evolve. This is crucial for maintaining reliability in production environments. We can also perform advanced data quality checks with Great Expectations. Great Expectations is a powerful tool for defining and automating data quality checks. It provides an intuitive way to set expectations for data sets and validate them against those rules. In our script, we load the Titanic dataset into Great Expectations context for validation. Expectations are created to ensure that the passenger ID values are non-null and unique, and that the age and fare columns belong in valid ranges. The dataset is validated against these expectations, and the results are logged to identify any violations, such as the missing values or invalid categories. Automating quality checks ensures datasets are always compliant with code standards, even as new data is introduced. Static code analysis with Flake8. Static code analysis evaluates your code for error, potential issues, and adherence to style guides without actually executing it. Tools like Flake8 help identify violations of Python's PEP8 style guide. Code is scanned for issues like improper indentation, overly long lines, or unused imports. Errors such as undefined variables or incorrect functions calls are also flagged before runtime. Also, suggestions are made for refactoring code, making it maintainable and easier for collaboration. In our code, we create a mock file which has a lot of errors. After running the Flake8 command, we're able to see that these errors are shown. After we make these corrections, we see that errors are no longer visible. Validation ensures your datasets are accurate, complete, and consistent. Testing with unit tests confirms pipeline functions perform as expected. Advanced tools like Great Expectation automate query checks, making them repeatable and scalable. Static code with Flake8 ensures clean and maintainable code. These practices enhance reliability and reduce errors in production pipelines. In section 13, we'll be exploring how we can structure, maintain, and deploy Python packages. Packaging your code makes it reusable and shareable, whether within your organization or in a broader Python community. By the end of this section, you'll understand how to structure a Python package, how to define a setup file for package metadata, how to build and test a package locally, and how to prepare it for distribution. A Python package is a directory containing Python modules, that is files with .py extension, along with an init file to indicate that it's a package. Your package is usually structured as follows. Data quality analytics vector contains your main package code. Init indicates that this directory is a package. ETL.py includes all ETL related functions such as transforming and loading data. Quality checks contains functions for validating data quality. Test holds unit tests to ensure your package functions are as expected. The readme.md provides documentation about the package. Setup.py defines the package metadata and dependencies. A clear structure makes your package maintainable and user-friendly. It allows developers to easily contribute to your code base. Now define the setup.py file, which is the heart of your Python package. It contains metadata about your package, that is the name, version, author, and specifies dependencies required to work. The package metadata includes the package name, version, description, author, and contact information. Dependencies list libraries such as Pandas that are needed. Python version specifies the minimum Python version that the package supports. A well-defined setup.py ensures that users can install your package and dependencies efficiently. Building a package creates a distributable version of your package. These files can be shared with others and uploaded to code repositories. We use building tools, that is the build module, to generate a package distribution file. A generated file is in a source archive format or a wheel format that is created. The wheel file format is optimized for easy installation. In our script, we simply change the package directory and we use the Python mbuild to generate these distribution files. We also test our package locally before we actually distribute it. It's very important to do local tests, such as installing locally and trying to use the functions. Thank you for joining me on this journey. Over the coming weeks, I'll be adding more videos on SQL, PySpark, and databases to deepen your data engineering skills. Be sure to also check out my data engineering career playlist for insights on job trends, skills needed, and career tips. Don't forget to subscribe for advanced tutorials, projects, and career insights. The continued practice and curiosity you well on your path to becoming a skilled data engineer. Until next time, good day.